Deep underwater, off the Pacific Northwest, lies an ancient danger. Once triggered, it would spell disaster for the coastal community. It can't be stopped. All we can do is warn those in its path. The danger is real, with warnings written into the coastal landscape. In the early 90s, the Pacific Northwest was ravaged by intense storms.
And one of those effects was that a lot of mud was swept away from those storm systems, and what was found in those coastal regions were so-called ghost forests. And these are old coastal forests that existed once there. And so we can actually date this by looking at the tree rings and compare them to nearby forests, and then determine that these forests were destroyed by a tsunami event in 1700.
This area, called the Cascadia Subduction Zone, was witness to a terrible disaster. And evidence from the ghost forests reveal this catastrophe was not an isolated event, but part of a troubling pattern.
When we look at historical evidence, we know that Cascadia has ruptured every 250 to 500 years or so. And so we expect a significant risk for a new rupture and earthquake and tsunami to happen in the next 50 years.
We don't have to imagine what the effects of this disaster might look like today. In 2011, a magnitude 9.0 earthquake off the Japanese coast triggered a massive wave which killed more than 18,000 people. Japan has since installed an undersea sensor network to aid in early warning. The benefits of such a system in the Pacific Northwest are clear.
All right, so here's how the system works. An earthquake happens. We have sensors on the seafloor that sense that earthquake. They sense the pressure difference, the vibration. Our system can then take this data, just in number of points, 200 sensors or whatever they are, and extrapolate what is the motion of the whole seafloor, how the whole seafloor has moved. Once we know that, we know how water above it was displaced.
But sensing the water displacement is only one part of the system. Another challenge is calculating what happens next with the tsunami.
The movement of that displaced water, that becomes a tsunami, where it will hit the shore, when.
To forecast this, you need a highly detailed model of pre-calculated tsunami simulations to compare against the sensor data. This was the goal for a team from the University of Texas at Austin, UC San Diego, and Lawrence Livermore, to create a digital tsunami twin.
So we have an offline computation phase where we pre-compute the mappings between the seafloor motion and the observations and sensors, and that pre-computation can be used then in the online phase where the tsunami early warning is happening to infer from the pressure observations the seafloor motion, and then in just a fraction of a second forecast the tsunami wave.
This offline computation phase is more complicated than it sounds. To simulate the natural phenomena of a tsunami wave, scientists use a special type of math known as partial differential equations, or PDEs. These mathematical rules describe how things change in both time and space, and are crucial for translating nature into solvable equations. However, the sheer size of this simulation was daunting. The Cascadia Subduction Zone covers over 1,000 kilometers of complex undersea topography.
The seafloor varies very rapidly in the area where the plates are meeting, so in that area we have to be very careful modeling correctly the trench and the continental shelf and the deeper parts of the ocean with accurate measures.
To run a simulation at this scale and level of detail requires a massive number of equations, and scientists need a special way to solve them. That's where Lawrence Livermore National Laboratory's MFEM software comes in. MFEM, which stands for Modular Finite Element Methods, was designed to provide PDE solutions for mission-critical application codes. But MFEM's capabilities have also proven valuable for other scientific projects, like the Tsunami collaboration.
So MFEM starts with a description of the world, typically through a partial differential equation, and it makes the translation from PDE, partial differential equation, to computer language very seamless, easy, and powerful. That's why we think of it as an engine.
Although the pre-computation phase can be done on a smaller computing system, the team wanted to run this software engine on the most powerful hardware available to them, an exascale supercomputer. And in early 2025, a unique opportunity presented itself. The Capitan supercomputer had just been deployed, and before it was turned over for classified projects, there was a short window when researchers could try out its power on other major simulations. But these were untested waters. In this new exascale computing environment, a number of challenges still needed to be overcome. First, the MFEM engine had to be reconfigured to run on the supercomputer's GPUs to take advantage of their parallel processing power.
At a high level, CPUs and GPUs work really differently. A CPU is like a brain specialist. It loves big, complex chunk of work with a lot of silicon dedicated to smart decision making. A GPU, on the other hand, is made of thousands of much smaller cores that are incredibly fast, especially when they work all together in lockstep, accessing memory in a specific way. We had to recast the entire simulations. Instead of building one giant matrix and trying to invert it, that's the classic CPU-friendly approach, we broke the entire simulation down into a series of small GPU-friendly operations.
But to fully take advantage of Capitan's power, the Cascadia code didn't just have to be broken down, it also had to be scaled up.
One of the big motivations for us to run on LCAP was to try to scale our code on the biggest machines in the world. And LCAP was just made available, and we were lucky that we could get access and stress test our code and the machine at the same time.
The Cascadia team was able to run the simulation at much higher resolution and over zones larger than ever before. MFEM gave the Cascadia team the keys to El Capitan full power. We ran the largest problem the system was able to handle, with more than 1 billion of degrees of freedom per GPU.
Degrees of freedom signified the resolution at which we understand some critical phenomena. They're kind of like the pixels in your phone screen or your TV. The more pixels you have, the higher the resolution, the more accurate our understanding and our simulation is. A 4K TV is about 10 million pixels, so that's more than a million 4K TVs of understanding, detail, and resolution.
We ran a problem that is so big that we were pushing essentially every GPU was fully filled with data. So each GPU had more than 1 billion unknowns. And when you scale that to the whole system, they scaled to 55.5 trillion degrees of freedom. And to our knowledge, this was and still is the largest finite element, unstructured finite element simulation to date.
The achievement ushers in a new frontier for computational science. And it's not just a victory for tsunami forecasting. The algorithms created by the team can be applied to other disasters as well.
Those could, for example, include the tracking of wildfire, or, for example, the detection of contaminant spreading. And so similar algorithms apply there, where we could use digital twins for real-time tracking of those hazards.
These type of problems that if you approach them with more standard approaches would take years and years to solve are actually possible with the right tools and the right algorithmic approaches.
What really excites me is that this research could actually help save lives. decades of mathematical developments, years of software optimizations, and now with a handful of hours on El Capitan, all comes together to create a real-time digital twin that people could one day rely on.
At the moment, Cascadia is lacking the type of sensor instrumentation that we would need in order to implement and deploy a tsunami early warning framework that uses the high fidelity models that we want to use. So one of the questions we can now answer with our model is, given a certain budget for installing new instrumentations, new sensors, where would we optimally place these sensors along the Cascadia Subduction Zone in order to provide the most accurate forecasts?
The scientific community has taken note of this research and bestowed on the team one of its most prestigious honors.
The Gordon Bell Prize is the highest achievement granted in high-performance computing, and being recognized with this prize is a huge honor for me personally and for the entire team that was involved in this effort.
It shows the combination, again, of great ideas, great math, great software, and hardware engineering can produce something that truly matters.
Research is always hard. In fact, if it's too easy, you're probably doing something wrong or you're not aiming high enough. Everything that's really impressive, that's really worth striving for, it always comes at a cost. It's always difficult. It's always a bit of a process to push through. But that's what we do. We work here to solve challenging problems. That's why we come to work every day.